Oh, in this lecture, we're going to be discussing the means by which we will pass parameters to functions. And along with that, we're going to be introducing the idea of reference variables, which will be a little helpful later on as well in various uses of functions. And so we're going to start by looking at the way that the language C, the precursor to C++, dealt with parameter passing. There's two different ways that the language C had dealt with this, and both of them have their advantages and their disadvantages. And then we'll look at a third method by which we can pass parameters to functions, and that's going to be a way introduced by C++, and that will take some of the advantages of both methods and put them together, and that'll be sort of our third way of dealing with this. But we'll see then that there's the good of both is merged into one means of doing this. So we're going to start out by looking at a function called int minus 1, and this will be a very simple function. And all it's intended to do is take one integer, which we'll call old val, because we're going to be sending a value into this function, and it's just going to subtract 1 from it and return the value. So we'll say here old val equals old val minus 1, and then we're going to return old val. So this is about as simple as it gets. Now, when we call this function, what we're going to need to do is either send in a value or a variable holding an integer. So first thing we need to do is have a few variables to store results of the function and to store the value we're actually passing in. So let's say we have an integer myint, which we're going to store 31 in to start with, and also an integer second int, and in the beginning that won't have any particular value. And what we're going to do is make the function call second int equals int minus 1 of myint. So we'll send in myint as an argument to the function, and then old val we'll talk about in a second. We'll receive the value, and the result will be written into second int. So keep this in your mind or in your notes. And what I'm going to do now is draw a diagram of what's going on in memory. We've seen the memory diagrams a number of times by this point, back in the pointer lectures. And the way this gets set up for us inside memory is that we've got here whatever particular addresses we have in the function, some function that these were in, the myint and second int. So we say maybe it's at address 20, and here's myint, which has the value 31. And then perhaps at address 24, we have second int, which currently isn't storing anything, so we can write a question mark there to indicate that it's a, right now garbage value sitting in there. And now what we're going to do is call the function. So now we're going to run this line, second int equals int minus 1 of myint. And when we run that line, what's going to happen, as we've seen before, is a new section of memory, a new stack frame is set up for the function int minus 1. So these lines were presumably in some calling function. Then is the whatever other stuff might have gone on in there. This is the calling function, and now further down in memory will be minus 1, the called function. And so in this area now is going to be the variables, parameters, and such for int minus 1. And the only one we have is old val. A 60 or however low that address is, depending on how big the spot for declaring other variables was. And so inside old val, what happens now is, because of the code we saw earlier, which I can put back up here, when we send in the value of myint into this function, old val receives its value. So old val also has the value 31. And as we run this code now, old val has 1 subtracted from it. And then we return old val. And now that we return old val, that then is stored inside second int from the line of code we had up earlier, which was this one down here. Give the video a moment to center on. And so we're going to be writing the result into second int. And therefore, 30, the result of second int, now gets written into, or the result of the function now gets written into second int. The interesting thing about this procedure is you'll notice my int has not changed at all. We sent my int in as an argument to this function, and we messed around with the parameter that stored it, but you notice my int and old val are two entirely different memory locations. We copied the value of my int into old val. Therefore, when we made the subtraction, we are changing old val, a local variable, to int minus 1, rather than changing my int, a local variable of the calling function. So this is known as pass by value, because we're passing the value into the function rather than passing the variable itself. We can't change my int from int minus 1. We can only make use of the value and mess around with that value and return a new value, as we did here, but we can't actually change the original variable that held that value. So this is helpful, in a number of situations where we're just mainly worrying about manipulating numbers and not trying to change original variables. But unfortunately, there are also times when we would like to change the original values. We might want a function that's going to allow us to not only subtract 2 from our parameter, but also the original variable would be subtracted as well, or reduced. In other words, my int would have been changed to 30. And we don't have that here. So what we need is a second function. And this is also something that's available in the language C, the precursor to C++. And this is known as the phrase we're going to use it as is pass by pointer. I'll elaborate a little bit more later on the different types of passing and why they have the names they do. But we're going to call this pass by pointer. A distinctive name from what we're going to do in our third example. And the idea here is we have a similar function, except this time, just to distinguish it, we'll have int minus 2. And what this is going to take is an int pointer. So that means that the value we'll be sending into this function will be an address of an integer rather than an integer itself. Inside this function, then, once we have the address of the integer, in order to subtract values from that integer, we need to dereference the variable so we can obtain the integer itself. Because if all we have is the address stored in old val, then a dereference is necessary to obtain the value at that address. So we will write into the dereferenced old val, and we'll say that the value we're going to write into there will be equal to the value at the dereferenced old val minus 2. And then, once again, we're going to return an integer, and the integer we return is the integer located at the address stored in old val. So a third time, we need to dereference this. Now, the situation we have here is one where we need to send in an address instead. So we can likewise, as in the previous example, when we had pass by value, we had my int equals 31, and we had second int as another variable, and we passed in the variable itself. What we're going to do now is pass in the address of my int. We really have a couple different options for both of these first two examples. In this first example, we're passing in the value stored in my int. We could also have said second int equals int minus 1, 31. Because all that happens in this first line of code is that the value 31 is read from my int into the parameter. Now we're passing in the actual value itself rather than having to read it from a variable, but they're exactly equivalent for our purposes. We'll have the same kind of choice in the second example. The equivalent of the second line would be if we took the address directly and said second int equals int minus 2, and passed in the address of my int, and we've seen the address of operator before. The other part, this is the equivalent of sending in 31 when we have an integer parameter, And the reason is that the expression here, when it's evaluated, and expressions, of course, are always evaluated directly before we send in their single values in as arguments, the result of the evaluation of the expression address of my int will give us an actual address, one particular value. So that's essentially the same as sending in the value 31. If we wanted to send in a variable that held the address, we first need such a variable. So instead of doing things that way, we could have just as well said int pointer and then said my int pointer and then said my int pointer equals address of my int. So now whatever address that was, it was A20 in our previous example. It would then, that address would be stored in this variable, and then you can now say second int equals int minus 2, and then here my int pointer is our argument. So just as with the int minus 1 function, we could pass in a variable that holds our value or pass in the value directly. The same thing applies here. In this line down here, we're passing in the variable that holds the value. And in the line up here, we were instead passing in the value directly, the address value here. The only difference is now we have an address value we're sending in rather than an integer value. So in a way, the two examples aren't that different, because in both cases, we're sending in some value, we're storing the value in a parameter, and we're making use of that value. The difference is, in the first example, the value we were sending was the value we were concerned with, the integer. Here, we're in a sense sending things a level above the integer. We're sending the address. So even though the copying and the usage of the address works the same way as the copying and usage of the integer did before, what it means for our second example is because the address is the one being copied, we can then dereference that address and therefore obtain the integer in a manner different than we did the first time. And the consequences of this for our parameter passing are as follows. So keep this stuff in mind. And now let's look at the same diagram essentially we had before, where I have here, once again, A20 will be where my int is stored. A24 will be where second int is stored. And A28 will be where my int pointer was stored when we declared that variable. And so then we have whatever other stuff we have down here, because once again, there may have been a number of other declarations before we called the int minus 2 function. But what we have here now is this here is the calling function. And the stuff down here, then, as before, is the called function, which is, in this case, int minus 2. So what occurs here is, as before, 31 was written into my int. Second int we declared without initializing it, so there's a question mark there. And my int pointer received the address of my int, meaning this holds A20. And my int pointer, the address of my int, is what we sent in as an argument. So our old val here, the parameter of int minus 2, now stores A20 at whatever position that is. Because our parameter was an integer address value, not an integer value, it's now storing an integer address, not an integer. And because our parameter stores an integer address, now when you look at the int minus 2 code that we had up earlier, which I can put here, now when we look at this code, what we are doing in this case is dereferencing old val to get the value stored at the address stored in old val. So we say here A20 is the value stored inside old val. When I run a dereference on that value, I get the cell at A20, which we looked at before. That's this cell. So when I do the subtraction, what I'm saying is take this cell, or the value in this cell, and subtract 2 from it, meaning I get a 29 up here. Not down here. A 20 can't change any more than, or it could change, but we're not worrying about this. This is part of this local function just as much as old val was part of the local function int minus 1 in the last example. The difference here is because we're storing the address of a prior value rather than copying the prior value itself, now we can use that address to jump over to that prior value and change it. So instead of going directly to the value, I'm sort of using this pointer as a bridge, where I say, we won't send in the copy of the value directly, we'll send in the address. It's like me saying, instead of photocopying a term paper of mine to give to you so you can read it, I'm instead going to put the term paper in a post office box and then give you the location of that post office box, and you can go to that post office box and grab the original paper. I'm still not handing the paper to you directly. I'm still copying a value and such. But in this way, what I'm doing is I'm handing you a piece of paper with the address of the post office box on it, and you can then go to that address and read my original value. By using this third location, this third variable, the location of the post office box, I'm able to get you to the original value without having to give it to you directly. And that's what the ability we have here is. We have now changed the original value, and now when we return the dereferenced old val, we're then again going to this cell, dereferencing it to get the value 29, or rather going to this cell, dereferencing it to get the value 29, sending that back to be written into second int. So just as before, second int holds the ultimate result of the calculation. The difference here is that because we passed by pointer rather than passing by value, we are able to now have the myInt value altered, the myInt variable altered itself, rather than having the parameter value altered, but myInt stayed the same. So those are the two different means we had in C to deal with variables. We had the ability to pass by value, and we were able to pass by pointer. And these were your two abilities then. And the advantage of the top version, the pass by value, was that you've noticed the syntax is relatively simple. So if you weren't concerned with altering the variable, why go through all this extra nonsense? If you don't want to alter the variable to begin with, no big deal. Just use the top version. That was one reason you might want to use the top version, the pass by value. One reason you might want to use pass by pointer is because it gives you the facility to actually alter what you did before. You have the ability to alter your myInt by passing in its address instead of passing in its value itself. The downside is you've got a lot of extra syntax to worry about there. You have to make sure you dereference every time. Even one time that you forget to dereference could result in a compiler error, or as I've said before, that's if you're lucky. When you're dealing with pointers, when you're lucky, you get compiler errors. When you're unlucky, you actually write into the wrong portions of memory and such. So any sort of dealing with pointers can be an error-prone process. And so the third example we're going to look at sort of combines the best parts of both those features. We'll have a relatively simple syntax and yet have the ability to alter the variables of our calling functions. And there'll be other advantages as well, but we'll look at those after we look at example 3. So example 3 is going to make use of what is known as a reference variable or a reference parameter. The code here is int minus 3. And I'm going to leave a little bit of space here, and we'll see to start with that it's almost exactly like the first example, except, of course, we're subtracting 3. Old val equals old val minus 3, and then return old val. You'll notice this is almost exactly this, or right now, except from the minus 3 part instead of minus 1, it's exactly the same as the example 1. And we're going to add one last character to this to finish off the function, and that's an ampersand right after the int there. I mentioned before that different symbols will have different uses in different contexts, and here's a great example. When the ampersand comes before a variable name inside function code, then it means address of. When, on the other hand, the ampersand comes in the function header between a type and the variable, then it's signifying that what you've passed in is a reference variable, or that this parameter is a reference variable rather than a regular variable. And the question is, what's the difference between the two? And we will get to that question in just a second. But the thing I want you to make sure you understand before I draw anything else on here is that this ampersand does not mean address of here. And that can get very complicated for people, especially when, as we'll see some lectures in the future, when we have inside the parentheses a parameter such as this, where we might have int pointer reference, and then, you know, the variable old or whatever the variable name might have been. But the idea here is you can certainly have here star and ampersand right after each other. We'll talk about what that means later on. Don't worry about it for now. But what I want you to understand is that the ampersand here is something different than the ampersand right before a variable name inside the function braces, where we say address of. The ampersand here is different. And that's a point of confusion for a lot of students, which is why I'm repeating it 2 or 3 times now, so that you try and at least keep that in mind, that there's a difference between the ampersand inside the braces and the ampersand in the function header itself. So, that said, the idea here now is we still have our int, or my int, and our second int. And how do we call this? And here's going to be how we call this function. We have here second int equals int minus 3, and we pass in my int. There will not be a second alternative, and I'll explain why later on. So here's the one way we have to call this function. We pass in the variable itself, and as we saw before, we declared my int and set it to 31. We declared second int and didn't initialize it to anything. And now we're going to pass my int in as an argument to this function. This code is exactly like the first example. So you'll notice right away we don't have to do anything special to call this function. We don't need to pass in the ampersand before the variable name here, as we did for example 2. We don't need to store a new variable to store, or declare a new variable to store the address. We can deal with things exactly as we see them here. So right away things are simpler than example 2 and equally as complex as example 1, which is not too complex at all. What happens now when we deal with this, let's pull up another memory diagram. Is we have, once again, here A20 and A24 would be the addresses of int, which stores 31, and second int, which stores, make sure those dotted lines are clear because it'll be important this time. Second int, as always, stores nothing yet. And then what other variables we have declared we'll write into there. Here's the calling function. And now, continuing our memory diagram, we have here called function, which in this case is int minus 3 instead of int minus 2 or int minus 1. And the way to think about this, I mean, there's always, you know, some details we're hiding, but the way you should really view this is as if old val is not stored in memory. Old val here is not a separate variable. What old val is a renaming of the first variable. Or in other words, the way to think about this is that we have given one memory cell 2 different names. Inside the scope of the calling function, the name of the cell A20 is myInt. Inside the scope of the called function, int minus 3, the name of the cell A20 is oldVal. What this enables us to do is use 2 different names for the same location, 2 different variable names for the same location. And that's the idea of a reference variable. OldVal is known as a reference variable or reference parameter if you want to use it that way. And this is known as pass by reference. So we had pass by value and pass by pointer, and now we're passing by reference. That's our third example. And the idea here now is when I say in our code old val equals old val minus 3, well, since the name old val refers to a cell A20, I'm changing that value. And now when I return old val, 28 gets returned, and so 28 is written directly into second int, and we're done. The syntax is much like example 1, pretty straightforward. And yet the results are much like example 2, where we're able to actually alter the original variable. But we don't need to do that this time by passing the address and sort of using this bridge location. We're able to do that simply by saying, hey, whatever variable you're going to send me, I'm going to call it old val. And of course, the reason we have to do that is because we don't know what variable is being sent. This time, the call I made was second int equals int minus 3 with my int as the argument. But I could just as well have sent any variable I wanted in as the argument to this function. So in a way, old val is sort of an all-encompassing name that says, whatever variable you send me, I'm going to call it old int. Similar to, if you and I were secret agents involved in, dastardly spy plans, and you have various top secret couriers you're going to send to me to deliver packages. Now, you know who these couriers are, but I don't. Just as the calling function knows what variables it's sending into the function int minus 3, but int minus 3 doesn't have any idea what those names are because the scopes are different. So you're sending these people to my door, and I just call them agent because I don't know the person's name is Bob or Sue. I just look at this person and say, hello, agent, and this person knows that when I say agent, I must be referring to them because they're the only person in the doorway. So you send Bob with a package, and Bob shows up at my door, and I say, hello, agent, give me the package, and Bob does. And then a couple weeks later, you've hired Sue as another top secret courier because Bob came into ill effects. And so Sue sends the package to my door, or Sue comes to my door with the package, and I say, hello, agent, and Sue likewise knows I must be talking to her because she's the only one there. And so she hands me the package. And I can always refer to these people as agent, and it's clear what's going on. And the same thing applies with the functions here. No matter what variable you send in, whether it's my int or later on now that second int has a value, we could pass second int in as an argument to this function call. Whatever variable we want to send into this function call, int minus 3 doesn't need to know that variable name because int minus 3 says whatever variable is sent to me, I'm just going to call it old val. Whatever cell is being sent my way, I'm just going to refer to it as old val no matter what it was called before. Just like I call your courier agent no matter what their real name is. And that's what's going on here essentially. It's kind of a silly example, but I think it demonstrates the point somewhat in that we're simply saying int minus 3 can call your variable old val no matter what its real name is, my int or this int or second int or A or B or whatever else. No matter what you send in, the int minus 3 refers to it as old val. And therefore, you write your code in terms of old val, and you return old val, and you subtract 3 from old val, and everything works just fine. And the value at cell A20 is altered, and that value is sent back. And so that's how passing by reference works. And again, I stress here, old val is not stored here in memory as a separate variable. It simply should be thought of as a second name for the variable myInt, or the cell that myInt refers to. So the advantage here is that we are able to alter the variables we send in as arguments without having to use the messy pointer syntax. The syntax here is elegant and clean, and yet gives us the power we originally had in example 2. So those are your 3 types of parameter passing abilities you have in C++. You have the ability to pass by value, you have the ability to pass by pointer, and you have the ability to pass by reference. And passing by reference is quite common, especially when we have larger objects. So that's how that all works. Now the reason reference passing is more useful than what we've just seen here is, again, precisely because there's no copy that happens. We didn't have to copy 31 into a separate variable. We were able to just say, rename the cell that 31 is stored in. And that's especially helpful when we start sending around larger objects. If, for example, this had been at some location a large object, which I'll just abbreviate LOBJ, and then we wanted to store it inside here, so this was my object and second object, and this was located, say, at A20, and this was at A152, or something along those lines. And then we made a function call. Well, what would you rather do? I mean, if you're having your program deal with this object, would you rather make an entire copy of this down here to be referred to by some name? Or would you rather say, forget about the copy, I'm just going to rename the original cell? Reference variables enable us not only to alter the original variable, they also arrange things such that we don't need to waste the time making a copy of our value for the local function, nor do we need to waste the memory holding that copy. Because if this object took, as it does here, 142 cells, then that's 142 cells we're taking up here. And granted, it's a function. We will eventually return from it. But if you have a function A calls function B, which calls function C, which calls function D, and each of these functions has a lot of copies of various large objects, that starts to chew up memory relatively quickly. And so if you are going to keep making nested calls, for example, if you're doing something recursive and you're chewing up all that memory, you might well run out of memory before you're able to finish your computation. And so there is some advantage to be gained from having various functions use as little memory as possible. Plus, of course, as I said before, we've got the idea here that this large object, not only we don't have to take up the memory to copy the large object, but we don't need to take up the time to do it either. And if you're going to make a bunch of function calls, having to take those extra few microseconds to copy 142 cells worth of data rather than just indicating, okay, my old val should be a new address, or old val should refer to the same address, rather. In both of those cases, we have an advantage. We save not just the memory, but we save the time of not having to copy all the values in the 142 different cells here. We just make a new name to address mapping, and we're all set. So reference variables have that advantage as well. And that's why we will often see, and we'll notice this later, but you'll often see if this was our function header again, int -3, we could have also said const. Of course, this isn't going to work in our current example. Let me make this int -4 instead. If we were not going to do something like we did before, if all we were going to do is say return old val -4, and that way. This function, of course, is unlike int -3 and int -2 in that it does not change the original value. It's also unlike all of them in that it doesn't attempt to change any value. We're just making a computation here, but the result's not written back to anywhere, whether old val of int -1 or old val of int -2 or old val of int -3. In all those situations, we are trying to store the result somewhere and then return it. Now we're just returning it directly. But because we're not changing old val, there's no reason to allow ourselves the power to do that because we don't need it. We don't need that power. So you'll notice what happens here is we've now said, yes, it's a pass by reference, but it's a constant reference variable, which means don't bother copying your argument. Simply assign old val to be a second name for that same argument. But by putting the const here, we're also saying, warn me or let me know when I compile if somewhere in the code for this function I have happened to alter old val, because I'm telling myself in the function header that I don't want to alter old val. All I want to do here is say, well, old val will be a renaming for the purpose of saving memory. I don't need to make the copy and store it, and saving time. I simply don't need to make the copy. But I don't want the power to change old val. I just want the ability to have saved memory and time by not copying it. I want that second advantage, but the first advantage, the ability to actually change my parameter, I don't want. And so by putting a const in front of it, it's sort of a warning to you in that if the compiler sees that you have a const variable, and yet you've now said somewhere here old val equals old val minus 4, the compiler then says you can't change, you can't write into const variables. And that's your advantage here, is that you're forced to only do read operations on this variable and not a write. And you might say to yourself, well, I know in a function as simple as this, it's very clear to me that everything works okay. But in a much larger function, you may accidentally pass a reference variable up here intending to just read it. And yet later on in the code, 50 lines down, you may accidentally write it instead. So your intentions when you write the function header may be forgotten somewhere along the way by the time you get further down in the function. So this const, which is stripped away by the compiler, there's no machine operations on the actual hardware level that would keep a variable from being overwritten. But the compiler at least sees it as a check. And the const variable, which we'll look at a little bit later on, is helpful in many of those respects. There's a few different ways to use const, and they all involve basically you saying, listen, I know how this is intended to be used, so I'm going to enforce that by putting a const here. Now if I accidentally screw up later on in the function, there's still no problem, because the compiler will warn me, hey, you told yourself you're going to make things const here, so there's no point in trying to alter this when you've already told me it should be const. And so that's where the const keyword comes in as a sort of telling the compiler, tell me when I screw up. Where if you left that out, you could screw up and the compiler would not complain about it. So those are the two advantages of reference variables. We not only are able to alter the variables we send in as arguments, but it also saves time and memory in that we don't make copies of the arguments we send in. And so when we want to use that second feature, but not the first one, often we'll send things in as a const reference variable instead of just a reference variable itself. And for integers, it's not a big deal. You're not chewing up that much memory. But certainly, if you're passing in larger objects, it might be to your advantage to make your reference variables const rather than just regular reference variables. So with that said, the last thing we need to discuss is before we move on to just general idea of parameter passing, I want to go back and discuss or make sure everyone's clear on why it is that we only have one option here where we had two before. And the reason is if we just do something like this, before in the other examples we said, well, we do have the ability to pass in the variable. We also have the ability to pass in the value itself. And if you look at this, the question is, why can't we do this? I'm going to put a comment here to indicate that that code would not really be allowed. The question is, why not? And if you want to pause the tape and think about that, you're welcome to do so. The answer as to why not is that you have 31 here, and it's not a variable, so it can't be renamed. 31 is just a value. It would be hard-coded by the compiler upon compile time and sent in as the argument. And so there's no way to say that old val is a renaming of the cell holding 31 when 31 is not stored in any cell. It's a hard-coded number in your code. We haven't set aside any variable to store 31. So there's no renaming. It's like me trying to call the person at the door agent when all you've done is from your car thrown the package at my doorstep and driven off. And now I open the door, I see the package, and I say, hello agent, hand me the package, and there's no one there. You've sent me the information, but no one to hold it. And likewise here, we're sending in the information 31, but no variable to hold it. When there's no variable, it can't be renamed. Sometimes compilers will let you get away with that. They would say, they'd warn you and say, I'm creating a temporary variable to hold 31 just so I can rename it. But the idea is that's a problem, and the compiler should at least warn you, you probably didn't mean to do this, so I'm going to let you know I'm working around the problem, but I'm warning you that you might want to check your code because I'm suspecting you didn't mean to do this. But that's the problem here, is that you can't really send in hard-coded values because they can't be renamed. But variables that hold those values, variables can be renamed or given a second name. So unlike examples 1 and 2, you don't really have the option here of sending in a value or a variable holding it. You have to send in a variable. The other thing to concern ourselves with is the idea of what kind of terms are generally used for parameter passing. And this gets a bit into CS225, which you might get a chance to take at some future point. But generally, the terms that are used are pass by value allows you to, or does not allow you to, variables you send in to the parameter, and pass by reference. In that case, you can alter your parameter. When people talk about programming languages as a general topic, usually the discussion is pass by value versus pass by reference. You're sending things in so that they can't be altered versus sending things in so that they can be altered. And so what we basically have here is two different means of passing by reference. And so our first example, of course, we have said is pass by value. If we wanted to be very exact, we might say the second example is pass by reference using pointer variables. And the third example could be known as pass by reference using reference variables. And so if you're going to name those three examples that way, then we're making it clear in examples 2 and 3 that they're both pass by reference techniques. One of them uses the pointer variable to enable us to alter the integer. One of them uses reference variables to enable us to alter the integer. But the pointer and the reference variable, there are two different language implementations, both of which allow us to make things pass by reference, in terms of a general theoretical meaning of pass by reference. But we don't really need to concern ourselves too much with the general theoretical meaning of that in this class. And so that's why I said it is helpful to think of these respectively as pass by pointer for example 1, or pass by value rather, for example 1, pass by pointer for example 2, and pass by reference for example 3. We can think of those as sort of the slang or informal terms that we can use simply because there's not often a need for the formality of the full definition of example 2 and the full definition of example 3. So when I say pass by reference in this class, I'm going to mean specifically pass by reference variables. And if I want to use example 2, I'll say pass by pointer, and therefore you can assume when I say pass by reference, I mean using reference variables. But I just wanted to make you aware of that they're really, in terms of programming language theory, are just two ideas, pass by value and pass by reference. And what we basically have is two different implementations of the pass by reference idea. So that finishes up the discussion here on reference variables and passing parameters. And what we will talk about next time then is we'll start looking at class constructors and the different ideas behind constructors and what are known as the big three. And I'll leave things at that for now. So see you next lecture.